Everybody. So I wanted to kind of point out up front that channel sounding it's a new feature of Bluetooth. Expected to be ratified this year, but location services have always been a Bluetooth focus, right? Even from the inception, the idea of using advertisements for presence detection has been a feature of Bluetooth Low Energy. Adding to that, we started using RSSI to do very coarse ranging, to do an approximation of distance between two endpoints, and channel sounding could be viewed as an evolution, a next step in that to a fine ranging solution. And then on the other side, we also have seen direction finding using angle of arrival and angle of departure. That was adopted as part of the spec a number of years ago. So we'll go over some of this in greater detail in the slides that follow, but I just wanted to give a very quick overview. So channel sounding is a method of measuring distance between two connected Bluetooth Low Energy devices. It uses two modes of operation. We'll go into this further in the coming slides, but round trip time measurements and a phased-based ranging approach to measurement. And as I mentioned, it's only over connection, an active Bluetooth Low Energy connection. The specification includes the ability to use multiple antenna, up to 4 antenna paths for the scan. And there's multiple security features that are added to the standard to support channel sounding. We'll go over that later on in the presentation. And it's not mutually exclusive with angle of arrival or angle of departure, if some of you are familiar with direction finding. I'm going to be going fairly quickly through this slide deck, but just know the draft specification is public. It's available for download on the SIG website. But it's also important to note what isn't included in the spec. So I've gone over what we will see in the spec, but for instance, the spec stops basically at the link layer, right? It describes how two link layers communicate and generate IQ data that can be used in a distance estimation algorithm to resolve a distance. But the spec doesn't include any guidance really on how to architect that sort of algorithm, and it also doesn't include connectionless ranging. It's focused exclusively on connection-oriented rangings. Okay, so the next couple of slides just sort of go over the protocol features of channel sounding. To start with, let's just talk about everything that leads up to the point where a channel sounding procedure can begin. The first step is that LEACL encryption has to start. So this is an operation that can only happen over an encrypted connection. After that, there is a channel sounding security start where there is a DRBG secrets. Basically, bytes are passed back and forth to scramble, randomize the procedure that will follow. After that, the two endpoints communicate their capabilities. So capabilities here in this context include the modes, the submodes that are supported, the different timing characteristics, a number of antennas, that sort of thing. After capabilities are exchanged, there is a configuration that's proposed that has to be agreed upon that is based on common supported capabilities between the two endpoints. And then a procedure can start after that. I should say that not all of this is required before every channel sounding procedure. Capabilities get exchanged once, configurations can change over time. But this is all leading up to a point where a channel sounding procedure, where a distance estimation can happen. The procedure itself is broken down into more granular chunks. So a channel sounding procedure can consist of one or more events that consist each of one or more sub-events that consist of multiple steps. And the procedures and events the sub-events must happen within a single connection interval. And the steps, which is what we'll talk about mostly in the coming slides, are the actual kind of ranging procedure, right? That is either phase-based ranging or RTT, a time of flight, or a sort of a calibration step. So we'll go over those four modes in the next slide. So I mentioned these four modes. Calibration is this is a step that is used to basically compensate for expected clock drift between the two endpoints. It improves the accuracy of the IQ data that's being generated from the procedure. Mode 1 is round trip time. We're going to go through both round trip time and phase-based ranging in the next couple of slides, but round trip time essentially is taking time of flight, time of arrival, and time of departure between the two endpoints, between what's known as a reflector and initiator. Initiator is what starts a given step, and the reflector is sending either tones or sync packets back to the initiator. The mode 2 is phase-based ranging, and mode 3 is a combination of both PBR and RTT. We'll go through the advantages of that later, but it's important to note that mode 3 is an optional mode. A channel sounding device does not have to support mode 3, but mode 0 through 2 are required. So let's dig into RTT a bit. I think you may be familiar with RTT from other technologies, but essentially it is a method where an initiator transmits a sync packet that goes to the reflector. There's a timestamp, and then that is very quickly transmitted back from the reflector to the initiator. The significant security benefit of RTT packets is that time can't be reversed, right? So it prevents a reflector from appearing closer than it is. This is for malicious kind of relay attacks and things like that. And so the main benefit of using RTT is for this kind of added security feature. And there are optional features, optional operations within an RTT step where you can add random bits to a sync word. You can adjust the length of the packet in order to, again, try to minimize the potential for a relay attack. In mode 2, phase-based ranging, you're basically sweeping across the channel sound. The 2.4 gigahertz spectrum. Up to 72 channels can be used, and at each of those channels, all of the configured antenna paths are exercised. And so, key to remember is one step is in PBR is going to exercise each of those antenna paths. So, for instance, if you have a configuration with 4 antenna paths, there's going to be 4 exchanges between initiator and reflector per step. And the way this works is effectively there's a phase difference. There's a comparison of the transmitted phase to the received phase that happens, and that phase difference across the channel spectrum can be used to derive a distance. And the IQ data is transferred from reflector back to initiator just over the existing Bluetooth low energy link. So this is just to kind of round up, to roll up all of the sort of protocol pieces that we've looked at over the last couple of slides. That there's an initiation of a establishment of a Bluetooth connection. There's all the sort of setup work involved in encrypting the connection and setting up the two, comparing capabilities and choosing a configuration. And then in this case, phase-based ranging happens across a set of channels. We put 15 to 40 milliseconds here, but that can vary greatly depending on the configuration. And then the phase data is transferred back to the initiator. In this case, I've highlighted an access point and a sort of asset tag. We'll come back to this use case in the second part of the slide deck. So 2 other topics that are related to kind of protocol and the standard before we move on to those use cases. Just wanted to drill down really quickly on the antenna options. It's not required that multiple antennas be used for a channel sounding procedure. What we at Silicon Labs have found is that we see an improvement in the robustness and accuracy of the channel sounding procedure when you're using multiple antenna paths. And so I put this board on the screen as an example. This is actually a 30 by 30 millimeter board that has 2 PCB antennas, and even with a board of this size with antennas that are relatively small and not exactly optimally designed, we see a massive improvement in performance compared to a single antenna path is used. So improvement, when I say improvement, I mean in terms of performance when the board is in your back pocket, performance when a board is with the 2 boards are in an electrically noisy environment, for instance. And this is all, communicated during the capabilities and configuration. These configurations can change over time, and in some cases, maybe a system would want to use a single antenna versus multiple antennas, and that's okay as well. But just wanted to make it clear that the standard does prescribe how to communicate that multiple antennas are supported. And the other point I wanted to make, I've mentioned this a couple of times, security was viewed as adding security features to the standard was viewed as a priority with channel sounding from its inception. They wanted to make sure that we minimize the attack surface for spoofing and for sort of man-in-the-middle or relay attacks. The DRBG, the deterministic random bit generator, is kind of central to a lot of the security features for channel sounding. This, as I mentioned, is used during that initialization to scramble the data that goes across between the two endpoints during a procedure. And it can also do other things like randomize payloads and the size of the extensions. Another really interesting feature that's used in mode 3 and can also be used in mode 1 and mode 2 with sub-modes configurations is the ability to cross-check your PBR-based channel sounding results with RTT data. So you derive a highly accurate distance estimation using PBR, and then you check using the maybe slightly less accurate but still valid and trustworthy RTT data to make sure that the data you've derived matches kind of the reality that's specified by the timestamps. So, and the last thing I'll mention is the normalized attack detector metric, the NADM, which is it's basically a metric that allows the link layer to communicate to the higher layers of an application the likeliness that a bit has been manipulated during transmission, that there's some unusual kind of phase shifting activity that's happened. It's basically just a way to communicate that there may or very likely could have been some sort of interference, some sort of malicious interference with the signal. The standard doesn't really prescribe how to determine these things, but it just communicates what that scale is supposed to look like in terms of the numeric scale of how to communicate that something is likely to have happened versus not likely to have happened. Okay, so now that we've kind of gone through some of the protocol features of channel sounding, I want to just take one step back and mention, at the top of this presentation, I talked about how, location services have always been a priority for Bluetooth Low Energy. And I don't want to go through each of these, but just highlight a couple. If you look at RSSI versus angle of arrival versus channel sounding, both RSSI and angle of arrival have a connectionless mode of operation. Channel sounding is connection-oriented only, right? That in some cases, and we'll go through some of the sort of limitations of channel sounding as it's spec'd toward the end of the presentation, but that does present a scalability limitation, right? If you are only dealing with the number of devices that can be connected at a time, that is definitely a limitation compared to a connectionless one-to-many approach to ranging or to doing direction finding. There's also a significant improvement in accuracy between RSSI and channel sounding. RSSI can easily get plus or minus 5 meters of error or more, depending on just how challenging the environment is, whereas we see 0.3 to 0.5 meters of error in most cases. And that, of course, depends on a number of factors, including the kind of algorithm you're using, how much CPU or MCU bandwidth you're using to generate, to resolve a distance estimation metric. Okay, so just wanted to kind of highlight these are not meant to one that should not be replacing another. RSSI is absolutely ubiquitous, right? It's any Bluetooth Low Energy device that's out there today is going to support generation of an RSSI metric. Channel sounding may well become as ubiquitous as RSSI over time, but we're a long way from that. And of course, angle of arrival really is serving a different purpose, right? It's giving you direction finding information from which you can derive, if you are triangulating, a distance metric as well. Okay, so in the second half of this presentation, I wanted to dig into a couple of the use cases that we'll be seeing as channel sounding gets ratified. One way I think to break down these use cases broadly is between proximity awareness and locating solutions. So on the left-hand side of the screen, looking at proximity awareness, that includes both IoT and automotive use cases. So we're talking about door locks, I think access control, keyless entry, I think PEPs, passive entry, passive start, kind of automotive applications, building access systems, geofencing, zonal detection, that sort of thing. And then locating solutions, this would be asset management, tracking assets through a space, and other kind of consumer applications like pet finding and item finding applications. So to dig into sort of an asset, this actually combines both use cases. Let's say in a healthcare facility, if you are enabling channel sounding, say on the enterprise access points that are across a floor of a hospital, you can then apply access controls to sensitive areas where certain people aren't supposed to have access. You can track high-value assets through the space. If you have, mobile devices, on carts rolling around the floor, you can have these enterprise access points that are stationary, track, where an item is over time, and feed that to, a central kind of a security location to track assets. Just to dig into the enterprise access point use case. So I just mentioned sort of asset tracking using the enterprise access points. There's another value to adding channel sounding the enterprise access points. FCC regulations state that there has to be some transmit power adjustments based on the proximity of one access point to another. And if channel sounding is enabled in these access points, it's a very low overhead method to determining the distance between one access point and another. So this is a case where you can deploy channel sounding to do a number of things. It solves a number of problems at once. And then to add just one more layer to that, if you build out a system that also has a connection to a GPS data, you can then create a system that has absolute location tracking of devices of assets inside in an indoor space where the sort of GPS coordinates are locking a collection of enterprise access points to a place on Earth, and then those items can be tracked within that space. So this is kind of a logical endpoint to just how far out you can expand the sort of access asset tracking. Okay, another use case example, and I mentioned this kind of broadly, is the sort of zonal detection you can use for passive entry, passive start. So this would be vehicle access when you have a key fob or a phone left in your pocket, and as you approach, you cross certain thresholds based on one or more stationary access points, anchor points in a car, and using this sort of zonal detection, you can unlock a car, you can after authentication happens, right? You can unlock a car, you can start a car. This can be used in a single access point, say on the hood of the car, or multiple access points spanning the car. That, of course, adds complexity where each access point needs to sort of coordinate with one another and potentially hand off a BLE connection between access points or operate multiple anchor points simultaneously. And then to add further complexity to this use case, this could very likely, if you see, for instance, what the Car Connectivity Consortium has promoted, add UWB and NFC to the same system in a coordinated approach to passive entry, passive start. So just to kind of drill into secure car access slightly, there's one way of slicing all of the sort of use cases within the subcases within that use case is BLE only versus BLE plus UWB for ranging. So in the BLE only use case, the Bluetooth Low Energy anchors and the key fob or the phones that's used for the data channel to to perform authentication, but it's also used for channel sounding optionally. Could be using RSSI, or more likely we'll be using fine ranging with channel sounding. On the other side of the sort of use cases, using UWB for the sort of final and the sort of ultimate ranging in the system. But even in that use case, potentially channel sounding could be used as a sort of a first step to do an initial localization of the key fob or the phone relative to the car before UWB is engaged. And just to drill in a little bit further to kind of some of the implementations of this that we've seen. Let's say you have a car with multiple anchors, and in this system, one anchor point or all anchor points could be using RSSI to get a very coarse kind of presence detection, and then one or more of the sort of the anchors that are determined to be closest to the key fob could establish a connection with that key fob or that phone, and then channel sounding ranging could begin. So in that case, you're basically doing a lot of passive monitoring using RSSI before you're selectively enabling channel sounding to get more precision ranging. Okay, so I wanted to kind of end the presentation by talking about some of the limitations we've seen with channel sounding and some of the workarounds that we think are viable. So first of all, scalability. I mentioned scalability earlier in this presentation. Because it's connection oriented, you're especially with resource limited MCUs, you're going to hit an upper limit of the number of devices you can simultaneously scan, perform channel sounding procedures with. So broadly speaking, the way to kind of work around that is to be very selective about the connections that you establish. One way to do that is to use an accelerometer. When something isn't moving, when two objects are stationary, presumably you've already done ranging with those two objects, you know where they are, you should end the connection, go into a low power state, and only wake when motion is detected. And then that's sort of being very selective about the connections you make. And then another way to potentially improve the maximum number of devices that you can simultaneously scan is use a longer connection interval. This helps with unsynchronized multiple devices that are communicating with each other. It prevents or minimizes the chances of collisions. Another limitation is current draw. There's just a certain amount of current draw associated with an active BLE connection because you're, for every connection interval, doing some sort of transmission, doing some sort of reception. Again, an accelerometer could be used here to just limit the amount of time you spend in a higher power state in a connection. You could also selectively limit your transmit power. If you know you are within a certain proximity, it would be possible to dynamically adjust your transmit power. And you could also tweak other configurations in the procedure, such as limiting the number of channels you scan across. So if you are using 40 channels instead of 72, for instance, you are going to complete your PVR scan faster and use less current, right? So this could improve the battery life of your coin cell battery, etc. Another limitation is that we've talked about with the hospital floor that presumes that you have multiple access points across a very wide space, and a given asset is not going to be connected to every access point at the same time. So effectively, your access points just have to be smart enough to selectively communicate only with devices that they know are in a certain proximity, either using RSSI or using channel sounding as a temporary solution until motion is no longer detected, for instance, and also being able to transfer a BLE connection through a secrets exchange between one access point and another can help to improve or limit the likelihood of dropped connections and missing assets and reduction of user experience. And finally, there's this push and pull between accuracy of a channel sounding distance estimation output and the update rate, right? If you are scanning at 72 channels, you use 4 antenna paths. This takes quite a bit longer to complete a scan than if you are using a single antenna path with, say, 40 or fewer channels. But this is actually, I wouldn't even necessarily call this a limitation, even though that's what I did call it on screen here. It's more of a, this is a feature, right? This is how configurable channel sounding is as a specification. You can determine what you want to prioritize, whether it is maximizing your update rate or maximizing your accuracy. And you can also do that dynamically, right? That setup step that we saw after a capabilities exchange, you can choose the configuration for a given procedure based on the circumstances that the operational state you find yourself in. And so over time you can adjust between, I need, an object, say, is determined to be moving quickly, so I'm going to dial back the accuracy and improve the update rate so I can make sure to at least coarsely track a fast-moving object, for instance. Okay, so just to wrap up kind of with a few highlights. So what we see is that channel sounding is a substantial accuracy enhancement compared to RSSI. It's so substantial that it actually unlocks a set of use cases that just weren't feasible with RSSI. And also because security was considered from the inception of this standard, that helps to also unlock certain use cases such as passive entry, passive start in automotive, access control with door locks that wouldn't necessarily be appropriate for an RSSI-based approach to localization. And another key point here is that channel sounding is complementary to existing location services. Like I said, RSSI, ubiquitous and will remain so, and direction finding with angle of arrival, angle of departure is something that can be used in combination with channel sounding. Even other locationing solutions that are on the market today can work better together with channel sounding. And again, what we're seeing is that channel sounding spans an extremely wide variety of use cases. Like I mentioned, automotive and IoT use cases. And frankly, I don't think any of us that are working on channel sounding solutions today have a full view of the use cases. I don't think all the use cases have been thought of. As we see channel sounding functionality sort of spread out across product catalogs of multiple silicon vendors, customers are going to find ways of adding presence detection and zonal detection to their consumer products, to industrial applications that we haven't even thought of yet. That's one of the most exciting things about channel sounding, I think, is that it's going to be a feature add across the spectrum of Bluetooth low energy applications that we'll see as it kind of rolls out and matures in the coming years. So I'm looking forward to seeing what happens with channel sounding, and looking forward to see what everybody comes up with. That's all from my presentation.
For channel sounding, did we solve?